Jose, and I'll be presenting on the computational screening for cannabinoid type 2 receptor ligands. So what is the cannabinoid type 2 receptor? It is a GPCR encoded by the CNR2 gene. It has 7 alpha helices. It has possible therapeutic roles for the treatment of Alzheimer's, and it has been found that there's a downregulation in most diseases. It has a 44% homogeneity with CD1, and what this basically means is that there's a 45% similarity with the CD1 receptor, which is the most similar to this one. Where it is expressed in the brain, but it's mainly expressed in the autoimmune cells, in the GI system, the immune system, and the peripheral nervous system. Well, as you can see in the image, that would be the CB2 receptor with the 7 alpha helices. It has multiple binding sites, one of them being the orthosteric site. To this side, it binds the orthosteric agonist, which competes with the naturally produced 2-AG and AEA. And when this happens, basically it blocks them from binding to the receptor, and it creates all the intoxicating effects from CD1. So cannabis as a medicine conundrum, well, it has been widely used as recreational drug, but some of the pros are that it's a chronic pain reliever. It is used to decrease nausea in patients undergoing chemotherapy. It is a safer option compared to other opiates in pain management, and it is a natural compound, which means that it is easier to obtain rather than doing it in a lab. Some of the cons is that it affects short-term memory. It gives cognition impairment. This is why people are not allowed to drive while under influence. It produces lung damage as a result of the combustion, and depending on the state, it has a difference in legality. THC is one of the compounds responsible for most side effects, and this is because it produces the intoxication via cannabinoid type 1 receptor orthosteric binding. Our objective, we're looking for a novel compound to bind to the CB2 receptor, and those are 3 of them. The THC, as I said before, responsible for all the side effects, and the CP55, which is sold under the name Spice, that it was used as a tool compound for CB2, but it was found that it was very toxic. And WIN55 212 is another one of those 2 compounds that has been used to research CB2. So methods, basically what we did is that we selected 14 million compounds from the SIN20 database. This is a database that contains like billions of compounds, and you're allowed to put certain parameters to choose the ones that are just better to what you're investigating. So the next thing that we did is that we did a calculation of quick probe in Maestro. This basically what it shows is the toxicity of all the compounds, and we were able to reduce the number from 14 million to 7.5 million. Then we built a CB2 structure from the RCSB database with a PDB ID of 6 kpc. And when we introduced this to Maestro, we run HTDS, which stands for High-Throughput Virtual Screening, and that reduced our number from 7.5 million to 3 million. And as you can see in the image, there's a green box that is emboxing a compound. This is basically the co-crystallized ligand, and anything that was out of that box that didn't resemble that compound would be dropped, and that is why it drops from 7.5 million to 3 million in the high-throughput virtual screening. Next, we run the Glide SP that reduced the number to 450,000. This is a computational, it's a very computational heavy screening, so that is the reason why it dropped in such a big amount. And the next was a run Glide XP that reduced our number to 836 compounds. So basically what we did is that we created a huge filter with different jobs that reduced them to adjust them to the best compounds possible to use with the CB2 receptor. As you can see in this image, I know it is very crowded with a lot of white spots, blue spots, yellow spots. The blue lines and the yellow lines are the amino acids that interact and that bind the compound to the receptor, and the blue lines would be the pi sites, and this is a list of some of the amino acids that bind, and the yellow ones would be the hydrogen bonds connecting those two. And basically, as you can see, there are places where a lot more lines than others, and basically the more there are, the better it is able to connect. Scaffold grouping with the 836 compounds, we know that those were too many to further evaluate, so we noticed that many of them had similar structures, so we grouped them by chemical scaffold. Those 3 compounds are from the same scaffold, and as you can see, there are very little differences. Here having a double benzene ring, here a trifluoro, and the difference being here a methoxy with an alcohol. And then the difference between the first one and the third one just being the methoxy with the alcohol. So we ended up with 65 unique chemical scaffolds, so we reduced the number from 876 to those 65, as like probably groups of 5, 6, 7 compounds would end up having such a similar structure that they would end up in the same group. So scaffolds, those are 4 of the 65 scaffolds. As you can see, some of them are similar, some of them are very different, and under them there's some information about them. As Gavin noted before, the HERG being a number for toxicity, and the docking score being a number that we wanted to have more negative than -12, so anything below the -12.000 wouldn't be used. The HERG in his case was -6 or -7. In my case it was -5, so those 2 would not be used, while those 2 would be. In case we wanted to buy those compounds and try to test them later, this title, the zinc, and the rest of the numbers are the ones that we would search and to be able to buy them. So future research, we will purchase and test the compounds on an in vitro CB2 cell line to validate which compounds bind and activate the CB2 receptor. Acknowledgements, I'd like to thank the University of St. Joseph for holding the symposium day, and our lab, Dr. Brand, Karen Cabral, and Derek Rowan. I'll be happy to take any questions.
Just a couple of quick questions about the compounds that you ended up with. So you started with, well, you didn't start with obviously at 14 million, but you got down to 836 possible ligands that you could use that would fit into that binding site. And then you limited it down to
65 groups.
5, was it? And I noticed you had the very first line on those last 4 right there. The first line, that looks like they're all starting with a Z.
Yeah.
What are those title numbers? Are those your specific codes, or is there a code system for that? Because I haven't seen that.
You're talking about the zinc.
Yeah.
Yeah. That is a code specific to every single ligand, and basically what we do is that we go to a website that has them listed all by that code. So it is kind of like a universal type of coding.
Yeah, so it's some kind of a cool code where you can
Yeah.
basically somehow tell everyone exactly what you have, stereochemistry and everything.
Yeah, so
and
you
then
can just like
see if you can buy it.
If you type it, it will give you a list of options from different sellers, so that you can buy them, and depending on it, like it can be companies in Europe or the US.
Oh yeah, anyway, and they probably have to make them all. Okay. Just real quick, curious, because it would be a long time to even look at 65. Were any of them like right on or really close to other natural products?
So basically, the thing is that even though we got the 65 and we had filtered them according to Maestro and that, as they said before, and that logarithm, we also have noticed that with this data, from those 65, a lot of them we wouldn't have to use. So probably from those 65, we might reduce it to 20 for the next step.
Okay. I was just wondering if any of them were naturally occurring.
Derivatives.
Is that what it is?
Yeah.
So you
None of
could
them are
actually
natural
get a lot of
products,
these
but yeah.
pretty somewhat simple.
Yep. Yep. Derivatives.
That's all. Go ahead and cut up your U-boat and see what you can get.
Yes.
Just talk about receptors. It's always very interesting, how to bind to them or how to block them.
Mm-hmm.
And just looking into your presentation, I'm trying to think, this is computational model.
Yeah.
Then how much of the work you did on the computer collecting data? and how much you do in the lab. I'm just trying to understand, you know, how you
Yeah.
created this kind of that research and how you achieve that kind of that conclusion.
Yeah, so up to this point, it was all computational. So it was all run through Maestro. And as I said before, like when I showed you all the steps, well, I gotta go back. When I showed you all the steps, basically the next step would take more time than the one before. So going from 14 million to 7.5 million probably took us a couple hours. Whereas the last two steps, the Glide XP and SP, would take days or even weeks to do it, because even though we have really good computers, it is so heavy that it takes a lot of time.
Then what is your future regarding research?
So-
What year you are in?
I'm a junior
Okay.
right now. So right now I haven't decided. I would like to do a PhD, but I haven't really decided yet what I want to do, because there are so many options.
Okay. Okay. That sounds good. Okay, thank you.
I'll follow up on that line of questioning. So you've docked these molecules into your host protein. Do you have any indication whether these ligands are going to be agonists or antagonists or partial agonists? Do you have an idea what kind of induced fit, what kind of effects these will have on the parent protein? Go on, disagree with it. Why is Dr. Brand wrong?
That was surprising. Well, I wouldn't know how to respond to that. I mean, we were trying to research the orthosteric side,
Yeah.
and we were trying to look for orthosteric agonists. So I don't know if that responds to you in that sense.
Well, if you've got a nice big binding site, and normally your ligand goes in, the protein collapses around it, that's going to have consequences, right? But if you put the perfect fit molecule, that's going to probably be a really high potency antagonist, because nothing's going to change. So that's what I was looking for. And then the last question is, CB2 has so many diverse actions in the body.
Mhm.
So you must have a favorite molecule, and so what disease are you going to launch into your PhD, or your MD PhD? What are you going to cure with which one of those molecules? This is going to be an autoimmune, this is going to be immune, this is going to be GI. What are you going to cure?
I mean, what we noticed is that what I read about this was that it would be useful to treat depression, and I believe that is like an ongoing issue, and every single year there are more people suffering it. I haven't personally experienced it, but I knew that there was some kind of time where I wasn't as happy as I am. So it is something that interests me,
Very good.
and something I would like to investigate more. Any more questions? No.
Thank you.